We rely on it for, well, pretty much everything. It's this invisible energy that powers our entire world. But with all that incredible power comes some very real and honestly often misunderstood dangers. So today, we're going to pull back the curtain and look at what happens when electricity decides to break free. I mean, think about it. It charges our phones, it lights up our homes, it runs our entire civilization. But what happens when that force we depend on so much breaks the rules we've set for it? What happens when it turns against us? We flip a switch and the light just comes on. It feels so simple, so automatic. But to really truly understand the risks, we first have to get a handle on the fundamentals of how this invisible force actually behaves. And that all starts with a surprisingly simple law of physics. Yeah, it all comes down to this one elegant principle that explains pretty much everything you need to know about electrical hazards. It's called Ohm's law. Okay, here it is. Now don't worry, you don't need to be a physicist here, but just remember this one thing. The amount of current, that's the I in the equation, that's the part that makes electricity so dangerous. The more current, the bigger the problem. The absolute easiest way to think about this is to imagine water flowing through a pipe. Voltage, that's the water pressure pushing everything along. Current, that's how much water is actually flowing. And resistance, that's any kind of blockage in the pipe. So if you lower the resistance, clear out the blockage, the flow of current just skyrockets. And that, right there, is where the trouble really begins. So what happens when the pipe is you? Because under the wrong circumstances, your body can become part of an electrical circuit. It becomes the pathway. It becomes the conductor. Now, our bodies have a pretty cool built-in defense system, our skin. It acts as a natural insulator, right? It provides resistance to that electrical flow. But here's the catch. Its effectiveness isn't a constant. In fact, it can change in a split second. Just look at these numbers. If you touch a wire with a dry finger, your skin has a resistance of over 40,000 ohms. That's a pretty good blockage. But get that same finger wet, and your resistance drops all the way down to 4,000. And if you immerse your hand, whoa, it plummets to just a few hundred. So, going back to our water pipe analogy, being wet is like taking a stick of dynamite to that blockage in the pipe. You're just blowing it wide open. And this is how a situation that might have been harmless suddenly becomes incredibly dangerous, because now a massive amount of current can flow right through your body. With that resistance pretty much gone, the current just floods in. So what exactly is happening inside your body when that little zap turns into something far, far worse? Okay, see this number? 5 milliamps. It's a tiny, tiny amount of current. This is generally considered the maximum amount that's harmless to a person. You'd feel a slight tingle, and that's about it. No big deal. But what happens if you just increase that by a factor of 10? Just 10 times more. We get to 50 milliamps, and suddenly the situation isn't just a tingle anymore. It's life-threatening. The gap between a harmless shock and a fatal one is way smaller than most of us realize. At this level, the effects are absolutely brutal. The electricity causes your muscles to contract violently. This can lead to this terrifying thing called freezing, where your hand literally clamps down on a live wire and you physically can't let go. From there, it can cause your lungs to fail and send your heart into ventricular fibrillation, which is almost always fatal. But believe it or not, the dangers don't stop with shocks that travel through the body. At higher voltages, electricity can unleash its most devastating power of all, an arc flash. Now, this isn't electricity flowing through something. This is an explosion of electricity right through the air itself. This usually happens at 480 volts or more. When a circuit is accidentally shorted out, maybe someone drops a metal tool, for instance, the resistance drops to nearly zero. This causes a massive, instantaneous spike in current that just erupts into a blast of pure energy. And the heat from that blast is, well, it's almost unimaginable. An arc flash can reach temperatures of 35,000 degrees Fahrenheit. Let me put that into perspective for you. Welding is hot, right? That's about 3,000 degrees. The actual surface of the sun is 9,000 degrees. An arc flash is nearly 4 times hotter than the surface of the sun. It literally vaporizes metal and causes these devastating, completely unsurvivable burns. And it's not just the heat. The arc flash is immediately followed by an arc blast, a physical pressure wave. I'm talking about an explosion powerful enough to rupture eardrums, knock a person clear across a room, and if they happen to be breathing in at that exact moment, it can even collapse their lungs. So, knowing these absolutely extreme dangers, how can they possibly be managed? Well, the good news is, it often comes down to following some very simple rules that can make the difference between life and death. For people in industrial settings, a perfect example is something called the left-hand rule. It sounds a little strange, but there's a life-saving reason for every step. By standing to the side, using your non-dominant hand, and turning your body and face away, you're putting your vital organs as far as possible from the direct path of a potential blast. It's a simple procedure, but an incredibly important one. But for most of us, the single most important rule is this. The best defense for anyone who isn't a qualified professional is distance. That's it. Treat every exposed wire, every open electrical panel, as if it's live and incredibly dangerous, because there's a very good chance it is. Which really leaves us with one final question. Electricity is our constant companion, right? It's this invisible partner that makes modern life possible. But knowing its true power, are you giving it the respect it deserves?